The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, today I would like to do a Kinetic Monte Carlo example with you in class, and also talk a little bit about the connection between the master equation solution, the normal kinetic equations we use, and the how you handle these trajectories you'll get out of Kinetic Monte Carlo. All right, so let's just pick a simple example. As we mentioned, in the real world, it's pretty easy for these examples to get completely out of hand because the number of possible states can be so gigantic. And so I'll do a really super simple one here to try to keep that under hand, not worry about that. When you do the real problems, that will be a major issue, is that the number of states gets out of hand. So the simple example I'm going to do is a real one from inside your body. So inside your body, you have a thing called low-density lipoprotein, and there's little vesicles of fat, lipids, inside your body, actually, in your blood vessels. And these are bad. If you go to the doctor, they measure your LDL and your HDL, and if your LDL number is too high, then they yell at you for eating too much fat food, and they make you exercise and stuff like that. This has happened to me, so I know. And there's a reason for this, is because the LDL is susceptible to oxidation, and if too many of those lipid molecules peroxidize, it causes inflammation in your blood vessels, and that can cause your blood vessels to constrict and stuff that eventually can lead to heart attacks. And so that's why your doctor is alarmed if you have too much LDL, because it's just, you have a lot more material available that could be oxidized, that could kill you. There's actually a really complicated, interesting story about what vitamin E does in the LDL and how it interacts with vitamin C. And if you take my kinetics class, I'll tell you about that. But we'll do the simplest case now. We'll just do, if there's no vitamin E, there's no vitamin C, you just have some lipid and it's oxidizing, and let's model what's happening. So what you have is a little bubble of fat. So out here's water, and here's my fat, which I'll politely call lipid. That sounds like not quite as fat if you call it lipid. Slimming to call it lipid. And the lipid is susceptible to attack by this reaction. So if I have some peroxy radical, and I have the lipid molecules, which are some hydrocarbon, they can react and make peroxide plus a radical. And in your blood vessels, if you're not under the water or being killed, you have a lot of oxygen. And so the radicals, the carbon center radicals you form immediately react with oxygen to make the peroxy radical back. And so the net process, we can kind of combine these steps because this is super fast. So that's like a microsecond time scale for that to happen in your body because the oxygen concentration is so high in the blood. And so this reaction is really ROO plus RH plus O2 to ROOH plus ROO. So the radical is just catalyzing the oxidation of your lipid into the peroxide. When this level gets too high, then your body will detect it as inflammation and you'll have all kinds of trouble. Okay, so we'd like to understand this. Now these vesicles are very small, so there's a probability you might have only a very small number of radicals in there. Also, your body has a lot of antioxidants in it, like vitamin C, and vitamin E, and some other ones too. And the antioxidants are trying to get rid of radicals. So the number of radicals you'd expect, the concentration, background concentration is very tiny. And because of that, this is tiny and the concentration is tiny, so the concentration times the volume might also be tiny. So the total number of radicals might be very small. And so therefore you might need to worry about the stochastic kinetics being different than the continuum kinetics. Okay, so that's the idea. Now, on top of that, you also have a lot of these vesicles in your body. So you might be able to somehow work up some kind of continuum model treating them all. And in fact, I think that's what people did originally, is they just said, well, let's take the total amount of LDL you got in your body and do a continuum model. But as we'll see, it's different because of the fact that the vesicles are small. Each one might only have, say, one radical in it, and that will actually behave quite differently than if you had a lot of radicals. All right, so this is the kinetics, and the oxygen is almost always high concentration, so I'm not going to worry about that. And I'm going to assume that we're not going to let your lipid oxidize so much that the amount of lipid changes significantly. So let's just, for now, we can just ignore this. Okay, maybe later we might go back and figure out how you account for the fact that these cells are being consumed, which would change the rates a little bit. So we'll just assume that that concentration is constant. So you have a tiny amount of radicals, and if you have the radicals in your vesicle, they're creating ROH, and you see the RO is catalytic. And so what we're going to see is basically D. If you did it in classical kinetics, you'd write dR ddt of this is basically equal to some constant times ROO. Okay. Because this, and I lumped these concentrations into this constant appropriately. Okay. Is that all right? All right. So that's the important process. We also have another important process is that if you get two radicals in there and they bump into each other, they can kill each other off. So two peroxy radicals can combine to make stable molecules. And we don't care what stable molecules there really are. What's important is to get rid of the radicals, because the radicals are catalyzing the unfavorable oxidation. So this is, and I'm going to call, in this program I started writing, I call this K3, this one's K4, reaction 4. There's two other things happening. Is out here I had some peroxy radicals. They're floating around the water. Some of them might go into my lipid. I'll call that process K1. There's some time constant in which new radicals arrive. And then I also have the possibility these guys can diffuse out. So I'll call that K2. And K1 I'll just treat as a constant. So I assume there's a background concentration of radicals that's constant. And so this is just some, every 10 seconds or something, a radical arrives in a vesicle. And this will depend on the concentration of the number of ROs. Right, so the more you have inside here, the faster the rate at which they go out. Is that all right? And this is just mass transfer. But from the point of view of the equations, it doesn't care if it's mass transfer or chemical reaction. You write them the same way. All right. So that's the system. And so let's look at I started trying to write the MATLAB code for this, and maybe we can try to finish this together in class. So I have 4 processes: arrival of new radical, diffusion of the radical out of the vesicle, reaction to make the peroxide, and self-destruction of the radicals. Okay? And I wrote down what each of these does. So the first one increases the number of radicals by 1. The second one gets rid of a radical because it's diffused away. The third one increases the amount of peroxide. The last one gets rid of 2 radicals. Okay? So we're going to try to compute a trajectory by the Kinetic Monte Carlo method. And a trajectory is going to be some time points, the number of radicals at that time point, the number of peroxides I have at that time point. And as I run, I'm going to get many different time points, and each one will have a different number of radicals or a different number of peroxides. And that's what I want to compute. And then at the end, after I have trajectories like that, big tables of these things, I want to somehow put it together to figure out on average what happened or something that I'm trying to understand. All right. And so let's see. So my inputs are the initial numbers of radicals and peroxides in the vesicle, the vector of rate coefficients, the maximum amount of time I want to run the trajectory for, not clock time, but time in the simulation. So it's like how many microseconds or milliseconds or seconds I look at my lipid protein and see what it's doing. And the maximum number of steps, because I don't want to get a trajectory list that's 10 to the 9th long, because it might overwhelm my memory and my computer and cause me trouble. Okay? So here they are, all those setups. Everything's fine so far? So here's the loop. So the outermost loop is just to keep track of how many steps we have, which is going to be the number of entries we have in the trajectory table. And the second one is really what we care about is, well, the time is less than the maximum time in the simulation. First, we want to figure out the time step until something happens. So following Joe Scott's notes, we compute this quantity called A, which is the sort of the sum of all the rates. And that's equal to the rate of the first process, and then the rate of the second process, which depends on the number of radicals. And the rate of the third process also depends on the number of radicals. And the rate of the fourth process, which is the number of radicals times the number of radicals minus 1. Now, K4 has to have units of per second, but bimolecular rates would normally have units of volume per second, per mole even, volumes per molecule per second. And so that K4 has to really be a normal kind of K divided by the volume. And we're going to have to figure out what to do about that in a minute. All right, and then we do the formula to get the Gillespie's formula for how to sample from an exponential decay. Basically, that's what that is. And so it's sampling. So Gillespie thinks that the probability that something is going to happen, or the probability of the time until the next thing happens, is going as e to the negative a times t. That's the. So we're trying to sample from e to the negative at, and that's what that crazy log of the random number is doing. Is it's sampling from that distribution. And so we get a tau, so how long we've waited from the time the last thing happened until the next thing happened. And then we have to figure out what happened. So there's 4 different processes that could have happened. A radical could have arrived, a radical could have left, a radical could have reacted with one of my hydrocarbon molecules, one of my lipids, or the 2 radicals could have killed each other. So we list these guys out. A is the sum of all those processes. P1 is the probability that the first process happened, that a new radical arrived. So it's going to be the K for the first step divided by A. That one was 0 order because it's the stuff diffusing in from outside. So it's just a K of 1. The second one, probably the second step is K2 times NRAD. That's the rate of the second step divided by the total rate of all the processes. And I'm going to add that onto P1 to make a vector of possible things that can happen. So I'm going to pick a random number from 0 to 1. And I want to make a little bar. Here's the probability that the first process happened, and here's the probability that the second process happened, and here's the probability that the third process happened, and here's the probability that the fourth process happened. And I know that these guys have to add up to 1 because I've computed that something happened. All right? And so I'm going to try to compare my random number from 0 to 1 to these breaks and sort it out into these 4 possibilities, and then figure out which thing happened. Okay, so this is the second step of Gillespie's algorithm. All right, so maybe you guys can help me finish the code here. If you want to go to Broadway in Chicago, you can go there. All right. So I need to write the next one. So P3 is equal to P2 plus what? So step 3 is, sorry? Say again? K3. All right? And that's enough, right? So now I have to choose a random number. So say x is equal to rand. And then I have to say if x is less than P1, then something. What's it going to be? Yeah. Then step number 1 happened. So that means that n rad is equal to n rad plus 1. So would one radical transport it in? If x is less than P2, self. Okay. Is that good? LCF with no space, thank you. what happens here? So this would be n rad is equal to n rad minus 1.
It needs to be between P1 and P2.
I think the else will take care of that, right? Is this right? X is less than P3, then N ROH else and rad. Does that look right? Do I need an end? Semicolon instead of a colon. Thank you. That would be really bad. Yeah. All right. Yes, Vicky?
So in the first while loop, you have step size larger than that, and then inside the loop, you are adding on to your step size.
So that's not good. It should be less than. Huh? Thank you. Any more bugs?
I think you need spaces after the brackets, please.
Spaces after the brackets where? Down here? Better to write in a separate line? Okay. I can do that. It's easier to read anyway, so that's good. I definitely agree with that. Is that right? You like this? And with all these else ifs, I don't need any ends. Is that right? They go one after the other like that? No problem. Just one end at the end. That's good. All right. All right. So we're okay with this? We think this is going to work? Huh?
Your while loop on step should be
I got it. Yeah, good. Listen. All right. So now we've computed what's going to happen. Now we need to store our results somehow, right? So I'm going to say trajectory is equal to, or trajectory of steps. Let's see. So step was 0, now step is 1. I don't know what a step is 1 to start with. Yeah. Does this look good? Maybe I don't want commas. Is that right? No commas?
I think if you want step being 0 at the beginning, which will look advanced of the concept.
One step is 0 at the beginning. But I already have the first line filled in here.
Okay. Okay.
Is that okay? Okay. Well, we'll see. I don't know if it's okay or not, but I'll believe you. All right. All right. So right now we have a program with that maybe or maybe not might actually compute something. Is that right? Okay. Now we have to figure out what the initial how we're gonna run this program. So we need an initial. So any suggestions? All right, so let's do an initial. How about nrad is equal to 1 and nroh is equal to 0? Is that okay? We're cool with that? Okay. And how about k? So we need a vector of k's. Yep. Yes, thank you. Is that right? Yes? All right. So let's think about what's reasonable for the k's. So I think we can make the k for the stuff diffusing in very, very small. So I don't know what number we're going to make it small. It's 1e minus 5, something. So that's small. Only once an hour. It might be a little bit too small. And then the next one is how fast things diffuse out. Now, what's that going to physically depend on? It should be like something like the diffusion length to get back to the wall. get that back to the outside. So it should be by one radical in here, what's the average time for it to diffuse back out? Any ideas? So if it does say just a random walk, maybe, then you say that like delta x squared is like d times delta t. Is that right? Yeah. Okay, so delta x squared, maybe we make this like the radius of our lipid vesicle. So the delta t is like r squared over d. Seems like a reasonable scaling. And we actually want a rate, so we want it the other way around. So K2 is going to be something like d over r squared. All right, so we need to pick a size of our LDL vesicles. I don't actually know what they are. I used to know this, but I don't remember. Anybody want to make a guess? How big is a vesicle inside your blood vessel? Micron, okay. So let's pick a micron. So let's say r is equal to 10 to the minus 6 meters. What's a length scale? What's a diffusion constant in liquid phase? 10 to the fifth what units? 10 to the minus fifth meters squared per second. Okay, sounds reasonable. Anybody know if it's meter squared or centimeter squared? That's like, okay. What? You guys did the one with the drug. What was the drugs one? It was 10 to the minus 6 meters squared or centimeter squared? Meter squared. Okay, so meters. So for a lighter, smaller molecule, it's reasonable. Yeah. Okay. So this number should be something like 10 to the minus 5 divided by 10 to the minus 12, so something like 10 to the 7. Okay. One e to the 7. All right. Now for the reaction, ROO plus RH. We could go look it up on the NIST.gov. They'll have a list of reactions like that. And but for now, let's just guess. And so let's say that K3, K3, right? K of ROO plus RH. These guys typically have A factors of 10 to the 8th liters per mole second. And they have EAs about 15 kcals per mole over RT. Okay, so now we have to figure out how to turn this into the K3 we want. Now the K3 we want is really, K3 is like this. Times the concentration of the RH, because we took the RH out of the problem, right? Because it's really so we want this to have units of per second. Is that right? And this is in units of volume per meters cubed per mole second, and this would be moles per meter cubed. And so it's per second, which looks right. Okay, so now we need to have somebody, I know somebody with a calculator, we can try to calculate this number for room temperature. And this does not mean room temperature, this means R times T. Actually for body temperature. And the concentration of hydrocarbon, it's actually the number of H's, because every H can be attacked in the hydrocarbon. So you typically have densities of 0.8 grams per centimeter cubed, is for organic. And you typically have two H atoms per 14 grams of CH2 groups, because you all have CH2 groups in there. All right. So 2 H atoms. And then if we're going to try to keep moles here, we need 6 times 10 to the 23rd atoms per mole. All right, and this is centimeters cubed, but this one is liters, so I need 10 to the 3 centimeters cubed per liter. So again, verifying what your high school teacher taught you, that the first thing is to learn units. Unit conversions. All right? So we take all these numbers. This is the RH, and this is the K. And we can multiply them all together, and we should get something reasonable, maybe. And since we have MATLAB, we can make it do it for us. So let's just do that. So we think it's, you have to help me, I can't read this very well. 1e8 star exponential negative 15,000 slash 1.987 times, what's body temperature? 40 C or something? So it's 310 Kelvin, maybe. All right, times all these numbers. 0.8 times 2. Slash times, what's the last one? Oh, divide by 10 to the 23rd. Any more factors in there? 1,000. Okay, so 5 times 10 to the minus 25. We think we got this right? But I want to get moles, because I have this in moles. It's per mole H atom. H atoms, mole of H atoms. This is really mole of H atoms. Is this all right? Okay, so we'll try it. We'll see what happens. So 5 times 10 minus 25. It does seem pretty small, so we really have a problem. All right, and then the last reaction. Those reactions are typically 10 to the 5th liters per mole second. It's for a recombination of peroxy radicals. So now we have to get rid of the volume unit. Right, so this is for ROO. Sorry, I should write this more. Okay, so for this reaction, yep. Yes, question? No. One mole per gram. Very good. That's right, because a gram is not just 2 atoms, right? It's actually 2 moles. Yes? That will change this. Only a factor of 10 to the 23rd. All right, so we'll go back. Thank you. There we go, 0.3. That's more like it. All right. Okay, so now let's go and do the same thing with this one. RO plus ROO. So typically these reactions, the normal way they're written, are numbers that are about 10 to 5th liters per mole second for 2 radicals recombining. Okay. So now I need to figure out how can I change the volume here? And the key is I know the volume of this lipid particle. So what I really want is this, my K4 is going to be equal to normal K divided by the volume of the reactor. Because it's really the rate we would write normally, which would be d ROO dt, is it would be like negative 2 K ROO plus ROO times the number, well, the moles, the concentration of ROO squared, right? This is how we would normally write it. And so we have to have its units all right. So this is the volume of the reactor. So we're going to have, we were having N ROO over V, but we might need Avogadro's number here, right? Because we're, the rate here is in moles, but now we are going to do them single molecules. Yeah?
Do you ever actually use K4 in calculations?
Yeah, for A. I think in A it's there. Yeah. Yeah. Good question. All right. So we think this should be like a volume per molecule or something like that, or for one molecule. So this should be K4 should be 10 to the 5th liters per mole second divided by 4/3 pi r cubed. Right? And then we need a mole, 6 times 10 to the 23rd molecules. And we're going to have to make sure that the liters in these guys match up, which is not going to be so easy. So this is going to be in, you might use 10 to the minus 6 meters. This is going to be meters cubed. So I need 10 to the 3 liters per meter cubed. And I think that will all work out to be per second. So let's try it. So this would be 10 to the 5th over 4/3 pi is about 4. 10 to the negative 18. 6 times 10 to the 23rd. Yeah? So all the big ones cancel each other out. And so 1 over 24. What? Oh, I lost it. That's bad. Okay. So 1 over 24,000. Yeah? It's a lot easier to do it with a lot of people checking your work. All right, so 4 times 10 to the minus 5. So this is what we think K is. Yeah? Anything else we need? We need a T max. You want to guess a time? How long you want to wait? The time for the main reaction, the time constant is like seconds, right? So if we wait 1,000 seconds, a lot of stuff's going to happen, right? Yeah, so maybe 1,000 seconds would be okay for T max. So let's try this all. All right, so here's the main function. The main function. I decided my n initial was the simple 1, 0. Right. And K, we just decided was 1e minus 5, 1e7, 0.3, 4e minus 5. Now, if you just look at these rates for a second, I think you can see a problem we're going to have. How many steps do I do? I don't know. 10,000. The time scales here, this 1e7 is pretty fast. So the stuff's going to diffuse out of there, the radicals will disappear, and then nothing's going to happen. Yeah?
I looked at the diffusion coefficient, and I think that's kind of a negative centimeters squared.
Centimeters squared? I thought so, yeah. Okay, thank you. So we think this is 10 to the minus 9. So this is actually 4 orders of magnitude is lower. Is that right? We're still going to have a problem, but it's not quite bad as a problem. So let's fix that. So I think our problem is that the 1e minus 5 is actually too slow. So radicals are diffusing in from outside at some rate. And it's got to be a rate so that if there was no reaction, basically the concentrations of the stuff here and here might be about the same, right? Same order of magnitude of the stuff dissolved in the water, dissolved in the lipid. Maybe a couple orders of magnitude different, but not a million times different. And so we need to have the rate of this stuff coming in to be something reasonable that's going to be kind of consistent with having a chance of having some radical in here. So now we have to guess what we think the real outside world radical concentration is. So maybe, I don't know what, 1e minus 10 moles per liter? 1e minus 6 moles per liter? I don't know. Anybody have an idea? Any biologists here know how many free radicals you have in your body? They can measure it, right? So it can't be 0, right? People talk about reactive oxygen species in your body, ROS, yeah. Yeah, so I don't know what it is. 10 to the minus 6, maybe 10 to the minus 8. So we had the number for 1e3 is for going out from the so we have the rate leaving is 1e3 per second times the number in there divided by the volume. Really, right? Well, it's times the number. That's the rate that's leaving. But we would think of this as a K. I don't know how to think of this actually, but for sure the volume matters, right? So that in order for us to compute this, we use the R squared. Now, another way you look at this is say, well, it's diffusion times the gradient and the concentration. Sorry? Is that Avogadro's constant? Well, it's okay. So they only live in their little tiny thing for a millisecond, then they diffuse out. I think that actually sounds very reasonable. It's only a micron. It's a very tiny little thing. So the question is, how do we compute the reverse? So if we had stuff outside, and suppose we didn't have anything inside, we'd have some rate of diffusion of the radicals from the outside coming in, right? And so that would be, how do we think about it? It's really got to be the inverse of this. So if we think the time constant is 10 to the minus 3 a millisecond to come out, it's probably about a millisecond to come in, right? I don't know. If you think it's going to maintain whatever initial concentration we put there, one per volume, then it's got to be about the same. So this can't be as tiny as 10 to the minus 5. So if we think the average concentration is 1, then this should be 10 to the 3, I think. If we think the average concentration is 10, then this should be 10 to the 4. If we think the average concentration is 100, then this should be 10 to the 5. So let's try 10 to the 3. See what happens. So every millisecond, something comes in or goes out. Some radical comes in and out. All right? You guys buy this? Would you defend this to your boss? Or are you blaming Professor Green? All right. Here goes nothing. You think it's going to work? Line 29. What's wrong? What's wrong with that? Parentheses stuff? No. Maybe I didn't save the latest version. Let's try again. Ah, I didn't save the latest version. That's what it is. All right. Now here goes nothing. I don't want to do that. Don't want all this help. Leave me alone. All right. Trajectory. The first column is the times. So I'll use the x-axis. And this last column is the oxidation, right, the products. So let's see if anything peroxidized or not. And I'll do circles. Oh, it should have all these zeros, right? So how come it only show the plot that way? That's really weird. Try it again. The time. Time is t plus tau. I guess I can look at them. I can look at the actually what happened. So trajectory. So it only gives 2 points. That's why it looks like that. I don't know why it doesn't show the zeros. They all show on top of the origin there. So why did it only give us 2 points? Yeah. Also says. So it says I got 307 oxidations, but why 307 all of a sudden? That makes no sense, right? So because it should be one at a time. I should be seeing one at a time coming in.
So what is this displaying? Is it the first vector be times? Because
Yeah.
there's definitely non-linearity times there, which is kind of worrying. 0 times 1,000.
Yes. It's very worrying. Yes, I agree. So we have a bug, right? We have a bug. So where is our bug? This is where I need your help. Okay, guys. Let's figure out why didn't this work. So I'm stepping the steps, right? They're going up. I know what's wrong. I need this step thing inside the loop here. So all this, let's see if I can explain this. I'm storing them according to the step. But right now the while loop is just zipping around and then it ends at the step and just gets 1. So that's the problem. All right, let's try again. Is this going to work this time? You guys don't have any faith. Yeah, people say that scientists and engineers don't have any faith. But I think we have more faith than anybody else. We believe stuff like this is going to work. It's like, you know. It's doing something now. Who knows what? Yep.
You're controlling the time until your arrival time is some 10 minutes, but you're also controlling the number of steps.
Yeah, it's not good, right?
I feel like that's true.
Shouldn't have too many. Yeah, it's a very good point. I have a nested loop. It should not be, right?
You might want to only sample, you don't necessarily want to sample every arrival time. You might want to sample only at steps. So you might want to have 2, you don't necessarily want to log every single
Yes. Yes, I agree.
but I don't know if this is going to be the correct.
Okay, so let's see how we can fix this. So we really want, is it really a jump out? Is that right? If the number of steps gets too large, we just want to jump out, so we want to go to? What do you think? break. That's what we want. So while is not the correct thing to do here.
Wait, why would T if, okay.
So we're step in time. Every time we'll do the steps, and we just want to break. If step greater than max steps.
Why don't you do an and for the while loop? While t is less than 2 max and.
What happens if you do a while loop like that? Do you guys know? Does it work?
It'll work.
It'll work. Okay, that's easy. Double and. That's I tried it with and this morning. It didn't work, so that's why I stopped doing it. Stuff like that. It's kill you, doesn't it? All right, we got to run over the ends at the end.
I don't necessarily think this would work. Like, I just think that's actually having.
I think it's likely to cause a problem. Why it's taking 10 million years? So really, there's no reason it should be a nested loop, right?
Yeah.
Yeah.
I mean, I feel like the.
We'll try it. All right, try again. That was too fast. Try that again. That's not good. Let's see, we have flat here. Oh! Jumps to 1. That doesn't look very good. Try that again. Yeah. Boom. Oh, no, that was pretty interesting. So that looks more like what you expect, right? So that at some time steps, I have 1, 2, 3, or 4 or 5 radicals in this vesicle. I only have one time step where it goes up to 9. So I think this actually looks like what I expect. I should see it jumping up and down. Stuff goes in and out. Sometimes it reacts. Sometimes it goes away. So this one's correct. I don't know what happened to the other one. So I'll have to figure out what's wrong with that equation. All right. We're almost done time. What I wanted to talk about for just 1 minute is what are we going to do after we have this working? So we get this working. We have the trajectory. We really want to run 10,000 trajectories, right? Because all we're doing is sampling from the probability distribution of time. So we need to run zillions of them. So this whole thing we just wrote would be inside a loop that runs a lot of different cases. Because every time you run this, because of the random number, you're going to get a different trajectory. And what you care about is sort of some kind of average behavior. Or you might want to know what's the percentage chance that I'm going to be oxidized and die. So you might say, I want to count what fraction of the trajectories end up with number of peroxide greater than some number. That means I'm dead. And if that probability is too high, then I know I'm in big trouble. Okay? So that'd be one possible thing. You might have whatever objective function you want. But you need to run a lot to get good statistics for anything. So you're going to have to embed this whole calculation inside a loop. And then you're going to get a zillion of these trajectories out. And you need to figure out how are you going to analyze them in order to figure out what you want. Okay? So one way is if you could add the trajectories up. So I have a trajectory. Suppose I have the number of ROHs versus time. And I do it once, and I have none, and then I have 1, and then I have 2, and then I wait longer, and I get 3, and then I wait long, and 4, whatever, something like that. That's what it really looks like for one trajectory. And the next time I run it, it starts at a slightly different time. And this time it runs longer before something else happens. And then it gets here, and then maybe it goes over here. Right? And I have a lot of them like that. I have 10,000 trajectories that all look like that. So if I could add them, then I could do an average, right, to get an average trajectory. So that'd be one possible thing. Or I might want a histogram. So I might pick one time point. So like after 20 minutes, I want a histogram of what this looks like here, or here. Say, okay, I have, one of them has 4 peroxides and one has 5 peroxides. And the other 9,999, some of the 3, some of whatever. Yes, question?
In general, the stopping times are exponentially distributed. You're not going to get the same time.
You're not going to get the same time points. That's right. So see when the this first time it stopped. The first time point was here. Second time, the first time point was here, and they'll all be different. So one is I was asking a few of the students before the class started, what's the there's got to be a program in MATLAB that will let you generate these kind of plots with the flat lines, or even a linear interpolation would be okay too. But you need to have some way to add them up as continuous functions because they all have different time points. So that's one practical issue about it. Okay, because you want to pick some special time you care about, and you want to know what does this directory say, what does this directory say, but you actually only have numbers here. Just really you have that number and this number and this number. That's all you got, something like that. Yep.
You can plot like a amount of time to get to n amount of ROHs.
Yep.
And then that would give you a mean and standard deviation.
Okay. So you can plot versus time instead, right? That's right. So you just think of what you want. You're going to have all this trajectory information, and then you figure what do you want, and then what are you going to plot, and what are you trying to compute, and you might want to compute not only the number but the standard deviation of the number, because you don't know how many trajectories you have to run before that standard deviation is narrow enough that you'll be confident with it. So this is a general problem with this whole approach, is that what you're getting out are just samples of things that happen. It's just like if you were doing a Monte Carlo and you just got some of the energy values from the hydrogen peroxide calculation you guys did. You have 47 of those energy values. What are you going to do with that? So you have to figure out how you're going to take the output of this calculation. I mean, it's sampling from the real solution, so it should be okay. But what is it? How are you going to handle that and use it as a mean? So it's sort of like as if you ran a zillion experiments, and then what would you do with all that data? So that's like issue number one. Now, alternatively, you could rewrite this as the master equation and solve it as an ODE, in which case you'll get explicitly P of each of these n's, so n rad, n ROH time. Now this would be it would be continuous in principle, but actually the ODE solver gives you out random time points also, right? So you get a similar kind of thing out from the ODE solver, except it'll give you probability for every possible range of these guys. So if you have 1 radical, 2 radicals, 3 radicals, 4 radicals, 5 radicals, and number of peroxides from 1 to 1,000 or however many peroxides you get, you're going to get numbers. So you have all these numbers, all these probabilities at different times. Again, what are you going to do with that? So one thing people do a lot is they would plot, say, the number of ROHs versus time. So at different time points, compute the average over all your trajectories. Or if you have this solution, you can compute that as n ROH P sort of n ROH, something like this. You can have some kind of average computed that way. And either one are fine, but you have to think of what do you want. And then in both cases, you're probably interested in the dispersion, so you really want to worry about the n squared too. All right, we'll talk more about this on Monday. All right, and I posted a homework problem that was given last year about this for Kinetic Monte Carlo for catalysis. It's used a lot in heterogeneous catalysis. And if you have extra time, feel free to do the problem. It's a really good problem. Those of you who are feeling like you don't have any extra time and you're about to kill yourself, please don't kill yourself. And instead, just send an email to me or Professor Swan asking for an extension, and we can give you some more time to finish up the homeworks that's due tonight. All right. Talk to you later.